So I will talk about possible generalization of the Young-Mills theory. So my talk will contain extension of the Poincare algebra, and then on basis of this new algebra, you build by the standard procedure by Young-Mills procedure to using the gauge invariance. Actually, it was stressed today also that it allows to build the interactive theory. And then I will write the Lagrangian. I will calculate the 3-and-1 loop amplitudes. I will show that this higher spin Young-Mills boson also contribute to the asymptotic freedom. And then I will speculate about the appearance of this tensor gluons in the proton and how it influences the Grant unification. So this is a publication on this subject. There was a 2005, so almost 10 years ago, and there's articles in collaboration with Antoniadis and Lars Brink, and with also Konitopoulos. So I want to show first the article of Golfand and Lippmann, and there is, you see, the extension of the algebra of Poincare is carried out by following manner. We add to the generators P mu and M mu nu the B-spin generators W, and here you see the algebra. So we will do something similar, not similar, but so we will add generators, which is LA, lambda 1, lambda S. So this generator is symmetric. It is a bosonic generator. It has indices lambda 1, lambda S, which are Lorentz indices, and index A is isotopic index of internal symmetry. So you see these three commutators are the standard Poincare algebra. You have the laws how the translation generators and rotation generator acts on this generator. It says that it is translationary invariant generators, all of them, and that it is that they have the tensor of rank S. That this formula say, and this formula says that these generators fulfill the current algebra. So I will say that to write this relation, I was somehow, it was done by help of Ludwig Fadeev, who actually, he guessed that the transformation which I have actually is forming the current algebra. This algebra have some unusual properties. For example, if you take the generator and you shift it by the momentum this way, where P mu is a momentum operator, you will see that this is somehow like a gauge transformation. You shift the field by something which is proportional to the derivative. This invariance is off-shell, which means that P squared can take any values. Therefore, I will prefer to call this gauge generators. And it also says that if you will find some representation of these generators, they are defined by modular longitudinal term, because these terms are definitely longitudinal because they are proportional to the momentum. One of the first simple representation which can be found is written here. You see, we introduce the vector xi mu, and definitely these two formulas define the Poincare algebra. And as you see, there is an additional angular momentum operator, which acting on the xi definitely will give you the fact that this is a tensor of the rank S, very specific. It has also this LA, the generators, and therefore indeed it fulfills the current algebra. And you can also see that the transformation which was I showed in the previous transparencies is actually the transformation of this vector xi by shifting it by some alpha times q mu. So there it is indeed gauge generators. So this is a more specific representation where the vector xi mu is taken as a scalar parameter q multiplied by the momentum, and then two transfers, two vectors, polarization vectors, which are normal to the k, and phi and xi belongs to the cylinder. So this vector actually was introduced by Wigner in his articles. So I was able also to calculate the Killing forms. So you can see that this Killing form on the internal algebra is a standard. This is a Killing form for the Poincare algebra, is also standard. Then using the representation which I showed in the previous slide, you can calculate the product between p mu and m mu. They are orthogonal, and this is the Killing form on the Killing form of current algebra. So we have this algebra of internal algebra, this Poincare, and this I use this notation LGP, which means that it's unifying algebra of Lie group and Poincare group. So how to build now the gauge theory? So we will follow the procedure which we already celebrating today in this conference. So we will build Young-Mills field, which depends on now not just on the Lie algebra, the internal algebra, but on this extension, because we have the new generators which has isotopic indices, and we have also Lorentz indices. We have to add to our gauge field a new Lorentz indices, and therefore our gauge field depends as it should on the index mu, but there is mixture of internal and space-time indices, which is written here. And then we will build the field strength tensor in a standard manner, and we will build the Lagrangian in this way, where this is because we have the Killing form ready, so we can calculate the Lagrangian. So Lagrangian looks, and the field strength tensors look like you see here. This is a standard formula of Young and Mills. And you can see that we have now infinite many field strength tensors, which contain now tensor fields. In the given case, I just write the first non-trivial one. We have the tensor gauge fields of the rank 2. And you can see it's completely dictate the interaction, because it's a vector multiplied by the tensor. It is not tensor square, like let's say, like in gravity. It's not interaction of two particles of spin 2. It just tells you that interaction should contain the spin 1 and then of its excitations. So one can study the spectrum and to see that the spectrum of theory contains the Young-Mills boson with the helicity plus minus 1, tensor boson with a spin plus minus 2 and 0. This is a symmetric part, and this is antisymmetric part of the rank 2 tensor, which was A mu lambda. It was not symmetric, so it contains both fields. And then it goes plus minus 3, plus minus 1, plus minus 1. And it goes each time it changes by 2. So you see that 4, 2, 2, and so on. And the degeneracy is also written here. So this is a spectrum of your theory. It's like it's a remind you string theory, where the spectrum is infinite, but these are massless particles. So the interaction, if you square the field strength tensor, you see that it contains vertices interaction of the gauge field with two rank 2 tensors, or two Young-Mills boson with the two tensors. What is important that coupling constant is dimensionless, and it is the same as in Young-Mills theory. So with the use of technique of this, what is called BCFW formalism, together with my collaborator, with Georgiou, we was able to find a formula which is extension of Parquet-Taylor formula for gluons. So we have here gluons, n-2 gluons, and two tensor gluons. Because as you see, the vertex was the gluon can decay into two tensor gluons. There is this non-trivial amplitude, and you see that this term, which is 2s minus 2 at s equal 1, it's disappear, and that formula reduced to Parquet-Taylor formula. So because we knew this amplitude, endpoint amplitude, we can consider what is called collinear behavior. So we will see let's say two tensor gluons to be in parallel. In that case, the amplitude, endpoint particle, factorized into n-1, and what is called the splitting amplitude, which was introduced by Altarelli, Parisi, and others. So these are splitting probabilities. This is a probability of gluon splitting to tensor, tensor to splitting to gluon, and tensor to splitting to tensor. So as you see, it contains, essentially depends on the spin of the particles, which can be 0, 1, 2, 3. This I just want to show you the Altarelli, Parisi, and of course Gribov and Dakshitzer and Lipatov. This kernels was calculated. So this is a quark going to quark, quark going to gluon, gluon to quarks, and gluon amplitude. So this is somehow the formula which I show you. It gives these probabilities in terms of tensors. Now you have to generalize. We have to generalize if we think now that this partner of the gluon exists in the world. So we have to consider a situation when, let's say, because we knew that in the proton, half of the momentum is carried by the gluons. So, and if gluons can decay into two tensor gluons, then we will think that there is a non-zero density of the tensor gluons inside the proton. So if we think so, we should write how they involved with the q quadrat, with the q square. So this is the equation which is this is a change of the quark density as a function of transfer momentum q square, where q square t is equal actually logarithm of q square. And you see that this is a standard formula which exists in the Diglap equation. These two terms are also, but we have additional terms when the tensor can decay into the gluon and tensor. So therefore, we have to introduce the tensor density, the density of tensor gluons inside the proton. And we have also the density of tensor gluons are changing if the gluons can decay into the tensor, and there is like this term, gluon goes to gluon, the same is triple vertex tensor goes to tensor. Now, this means that coupling constant here, alpha t, which is here, now have the contribution from quark gluons and from tensor gluons, and we have to calculate that. That can be calculated in two different ways, completely disconnected one from another. One is the unitary approach. When you cut the diagrams, you take the two, three amplitude, you glue them, and then you conclude what is a one loop contribution. Or you can do with a method which is effective action, which was yesterday we have heard from Professor Ludwig Fadeev. And so the result is written here. Looks very, very simple. So we see that this the first coefficient of the Kalan-Szymanczyk beta function is equal 12s squared minus 1 multiply the Casimir operator divided by 12. So you can see here, if we substitute s equal to 1, we get 12 minus 1, which is 11. And that's a famous result, which was also quoted many times in this conference by Gross, Wilczek, Politzer. So because as you see, all the spins from 1 and 2 and 3, they have the same sign. It does not change the sign. So, which means that each of these boson 1, 2, with spin 1, 2, 3, 4, all integer spins contribute with negative sign to the evolution. I also calculated this in a different way, which actually I did it many years ago in my PhD in '77, and I was fortunate that it was published. So the result, you can ask what is the spectrum of the tensor gluon in the background chromomagnetic field, and you can see that this Pauli-Landau formula actually has this 2n plus 1, a standard one, and this plus minus 2s. So when s is equal to 1/2, you will get plus minus 1, which is a Landau level, what is called, right? And when it is s equal to 1, that's the Young-Mills theory, and that was a summation of this spectrum in '77 leads to effective Lagrangian, which is written here. But in this case, in higher spin, spectra is simply 2 times s. And if you proceed to follow the same way to calculate the effective Lagrangian, you will see that the coefficient in front of logarithm is equal to 12s squared minus 1 divided by 12p squared theta z. So this is a two different way of calculating the beta function. One is from completely different region, you know, this Diglap equation and so on, and another is just pure field theoretical calculation. That's also what both of them, I will say, field theoretical, but in any case, I was very happy that both results coincide. And then, because we have infinite many particles, and this is an unusual field theory, it's field theory of infinite many particles. It's remind what you will call the string field theory, because strings has, if you do the third quantization of the string, which is not yet done somehow in full scale, yes. So you will have some Lagrangian. I think that in one of the speeches, Witten was referring to this after the work of Gross and Mende, that one should find what is the basic symmetry of string theory and to write the Lagrangian. So there should be some gauge principle, string gauge field theory principle, right? So this is in parallel. It's not string theory, but it somehow goes in parallel. So the question is that then we have infinite many particles. They are running in the loop. They contribute into the beta functions 12s squared minus 1. And you have to understand how to sum these things. So because one of my collaborators did it many years ago, the summation in the string theory to calculate the critical dimension by summing some infinite sum. So I follow the same procedure. And if you sum, you come out not to infinity, but you come to 0. So the conclusion is that if this is all true, then somehow if all the tensor gluons are excited, the theory becomes conformal invariant. So I don't know if it's good or bad, but that's how it is. If you calculate, we did just a preliminary result. I show you that this is a quark, one of the quark distribution function, PDF, what is called Proton distribution function, and you can see one is the distribution of the quark distribution when the tensor gluons are off, or then tensor gluon of spin 2 is in. Then you have this modification of the curve. So there is another question. If inside the proton there is a additional tensor gluons, then the formula for spin sum rule should be modified. So we have this delta sigma is a contribution of quarks. This is a contribution of polarized gluons. If the gluons are polarized, they also contribute to the spin. There is, of course, the orbital momentum, but if there is a tensor gluons, then there should be some part associated with the tensor gluons. And it's a long story, but we succeeded to generalize the formula which was written by Altarelli and Ross, which has these two terms. One is the quarks. You see that not only quark contribute, but also there is a contribution coming from the gluon. That's what their discovery was. And actually, it also say it depends also on the density of gluons, which is a important question. What is the density of polarized gluons inside the proton? And you see that there is additional terms which is associated with the polarization of the tensor gluons. Because the running of coupling constant is changing, right? Because you have the beta function somehow increases. So I ask myself, what will happen if let's say tensor gluon of just spin 2 is excited, and then you calculate the standard thing, and you will see that unification happens much more earlier than than Planck scale, so or whatever it is, 100 TeV. That's another conclusion which comes out from these calculations. So this is a summary. So of the how much time I have? 7 minutes. Oh my God, I was very fast means. So so the first statement is that we have the beta function which includes the contribution of tensor gluons, which is written here. We suggest that some part of the momentum, which is we think that it's carried by the gluons, actually are divided between gluons and tensor gluons. So therefore, I show the proton with some density of tensor gluons. There is a unification because of the acceleration of symptotic freedom. The intersection is not exactly like this. They are not exactly cutting each other, but what I can claim that it happens in much lower scale than in standard cases, and then there is the contribution coming from tensor gluons in the polarized experiments. So, because it's a conference devoted to the Young-Mills theory, I also want to have somehow present my recollections of. So I was visiting the Chern Institute of Mathematics at his hometown and his home as well in Tianjin, and I see the calendar on the wall, and then I ask the guide, "What is this? Calendar?" And he say, "Oh, this is a calendar which was made is created by Professor Chern." And then I say, "Can I open it and make photos?" They say, "Yes, you can do." So I was listening one after another, and I was absolutely amazed. Each page is devoted to some mathematical discoveries. And then I was going through, and this was absolutely astonishing. I mean, I see this, the last November picture, and you can see here the face of Maxwell, and with Maxwell equation, face of Professor Young, with probably, I did not read the Chinese, but my grandson, actually, who has half Greek, half Chinese, so he was helping me a little bit to read these things. So this is for strong interaction, and the phase of Einstein associated with the gravity. And my interpretation, I don't know exactly what was interpretation of the author, but I am absolutely sure that what he wants to say, that all fundamental interactions are described by the gauge principle. That's what he wants probably to say in this, because what he shows here is 4 fundamental forces, and all of them are based on the gauge principle. So I think that it's really a beautiful thing. And this is a sort of, I think that somebody also showed this. I was a little bit disappointed that somebody also got this idea, but somehow unification on physics and mathematics, with 2 great men. Thank you very much. So radiation means the following. You can see from the calculations that they are preferred to be absolutely parallel to the gluons. They don't like to go in the normal. Therefore, let's say in 3-jet events, you cannot see, I don't think that it will produce additional jets and so on. So I think that it's still, I can point into the specific experiment which will really prove or disprove that the tensor gluons are inside the proton exist or not, but I'm thinking about that.
From a phenomenological point of view, in the rounding of alpha S, which has been measured with very detailed,
yes.
Do you see differences with
yes, I see. So
this beta function?
Yes, very good question. I think that was asked, Altarelli asked me, and some other people also asked about that. And I think that discussion with Mangano, we looked at the particle data group. So if you see from experiments, what is uncertainty of the beta function? So it is from 10 to 15%. So which means that with all experiments today, it's allowed some contribution from something else. So this 10-15% might be from tensor gluons or for something else, but I want to say that still there is some place where it can be. Not more than that, but inside. So as you see, when you put the spin 2, of course it's already from 11 goes to 58. So it's a dramatic change. But I don't know, maybe you will add more, or something happens. There is maybe some in front, there is some more coefficient, and you can put it inside this 10-15%. I did not know at the moment.